Bismillah ar-Rahman ar-Rahim. Assalamu alaikum dear students. I am Arif and I welcome you all in today's session. To access the notebook for today's session, you can access course page on my personal website arifpart.me. The other way is to download all the notebook files from course GitHub account arifpucit. And all the notebooks for this course are housed in this public data science repository. Well, this is the Jupyter Notebook dashboard running locally on my machine at port 8888. And here is the notebook for lecture number 6.12 of the 6th module, Overview of Machine Learning, for the course titled Tools and Techniques for Data Science. Well, today we are going to switch gear, and after 5 sessions on data pre-processing, we are going to move back to once again to linear regression and need to complete few topics of supervised machine learning using linear regression. So let's move on to the agenda of today's notebook. We will start with a quick recap of video lecture 6.6, where we did linear regression using Scikit-Learn on the advertising dataset. And after this, I will give you an overview of polynomial regression. We will generate a synthetic dataset having a single feature, and we'll first try to fit simple linear regression estimator on it. Then we will generate polynomial features using Scikit-Learn transformer on the same dataset, and we'll see that the model will give good performance with the degree of 2. Well, after giving you an idea and of course hands-on practical example on simple polynomial linear regression, we will have an in-depth discussion on bias-variance tradeoff, the overfitting, underfitting, and good fitting of supervised machine learning models, as well as I will give you an abstract view of different techniques used to prevent overfitting. Finally, at the end of today's session, we will apply polynomial linear regression on advertising dataset and compare the results with the standard linear regression we did in the beginning of this session. I think we have a lot to do today, so let's start playing. My dear friends, let me start with a quick 5 minutes recap of our video lecture 6.6, in which we practically perform linear regression on this advertising dataset using Scikit-Learn. So first, let me import the libraries that we will be using throughout this book. NumPy as NP, Pandas as PD, Matplotlibs, PyPlot as PLT, and Seaborn as SNS. Now let us use Pandas read CSV method to load the advertising dataset into a data frame. Great. So once again, a quick description of the data. So this dataset has 3 input feature columns showing the expenditures spent on TV, radio, and newspaper advertisements in thousands of rupees. The output column sales shows the number of items sold in 1000 units. And there are 200 total observations. My dear students, before applying a linear regression model on any dataset, we must make sure that the dataset satisfies these 4 assumptions. That is linear relationship, independence, homoscedasticity, and normality. And I think we have done all these in our video session 6.6, I think. So let me move ahead and do a train test split on this dataset. Well, by now we all know that the reason to do a train test split is to split the available dataset into 2 parts, and one part is called the training dataset, on which we train our supervised machine learning model, The other part is called the test dataset, which we don't show to our model during training, and we use it later to evaluate the trained model actually. So we separate the input features in a variable capital X, and this can be done by simply dropping the output column from the data frame. And similarly, we separate the output column in variable lowercase y. So I have executed it. Then we use the train test split method of the model selection module of Scikit-Learn by passing it the input feature X, the output column Y, the test size parameter of say 0.2, mentioning the fraction of test data, and finally the random state for reproducibility. This is important if you intend to use multiple algorithms and later want to compare their performance. And this method, of course, returns a 4-valued tuple containing the X train, X test, Y train, and Y test in the same exact order. So let's execute it. Since the total number of rows in our dataset are 200 and we have mentioned the test size as 0.2, so we have 160 rows each in X train and Y train, and the 40 rows each in X test and Y test. Okay. So next step is to train our model on this training dataset, and for this we simply import the linear regression model from the linear model family of Scikit-Learn, create its instance, and then call its fit method by passing it the X train and the Y train part of the dataset. Let me execute it. So now we have our trained model. Let's check out the model coefficients and the y-intercept. Well, the y-intercept or beta node has a value of 3.05, showing that if we spend nothing on advertisement, the sales will be of 3.05 units of items. Similarly, these beta 1, beta 2, beta 3 corresponds to the weight of TV, radio and newspapers. The very small negative coefficient corresponding to this newspaper ads shows that it will lower or maybe drop the sales. However, today we will see that how the interaction of these terms will add synergy and will give us better results in the later part of today's session. Anyways, let's evaluate using the test data. So once we are done with training of the model, my dear students, it is time to evaluate it using the test data, which the model has not seen. This is actually the representation of how the model might perform in the real world once deployed. And to do this, we simply call the predict method on the trained model and passing it the X test to get the predicted Y values. We then calculate the test residuals, that is the residual errors, by subtracting the Y test values from the Y predicted values. And my dear students, of course, in our video lecture 6.6, we discussed in depth the different valuation metrics that we use for regression algorithms, like mean absolute error, mean squared error, root mean squared error, R squared value, adjusted R squared value. So we have done all these, we have discussed all these with the pros and cons. I have once again mentioned all the formulas over here for your review. And in this code cell, I have calculated all these evaluation metrics. Let me simply execute it. Okay. Remember, we try to minimize the three errors. That is the mean absolute error, mean squared error, and the root mean squared error. Here, RMSE of 1.46 means that by average the model predictions are this much off from the real values. And since the mean of our sales column is around 14, So RMSE of 1.4 can be interpreted as roughly 10% error. Well, unlike the three error metrics, this R2 and adjusted R2 score tells the performance of our model, having possible values in the range of 0 to 1, I think, with 0 being the worst, of course. And the value of 0.917 for the R2 score means that 91.7% of the variance in the sales column of our advertising dataset is accounted for by the three input features: TV, radio, and newspaper. And finally, we also did the residual plot in video session 6.6. So this is the residual plot having residual errors along the vertical axis and the output column sales along the horizontal axis. Since the data points are almost randomly distributed around this red horizontal line at 0, therefore we can say that a linear regression model is appropriate for this data set. And my dear students, if this is not the case, then we should try some non-linear model. So this was the recap. We are done with the recap of linear regression. Now it is time to understand polynomial regression. My dear students, linear regression normally fits a straight line on a data set. But there are times when there do not exist a linear relationship between the input feature X and the output label Y. For a 2D dataset, this is easy to visualize as shown in these four scatter plots, where the relationship of X with Y is polynomial, as shown in this left top graph, logarithmic, exponential, and sinusoidal. No straight line can fit these data points properly, so we need to come up with a curvy line. Well, in today's session, we are mainly concerned about polynomial regression, which is a form of linear regression that estimates the relationship between X and Y as a nth degree polynomial in X. So, this equation, let me describe this equation now. This first equation is a linear polynomial equation as the degree of X is 1. This is quite known to us. Y is equal to bx plus c. This is the equation of a straight line. This second equation, y is equal to ax square plus bx plus c, is a quadratic polynomial as the degree of X is 2. This third equation, y is equal to ax cube plus bx square plus cx plus d, is a cubic polynomial as the degree of X is 3. In the same fashion, we can have equation up to the nth degree. The data set in this graph, in this scatter plot on the top left, seems to be a third degree polynomial. And remember, the most prominent power, of course, influences the shape of the graph. That is the degree of 3. Okay, my dear students, let me move ahead and try to fit a line on a 2D dataset where the relationship between the single input feature X and the output label Y is non-linear. Let me generate a synthetic dataset using this quadratic polynomial equation of degree 2. Y is equal to 0.8 x square plus 0.9 x plus 2. Okay, so this seed method is usually used for reproducibility. This RAND method will generate an array of 100 rows and one column with random samples from uniform distribution. I am multiplying every value with 6 and subtracting from 3 to have values in the range of -3 to +3, both not inclusive. This line of code is actually generating 100 y values for each x value using the equation y is equal to 0.8 x square plus 0.9 x plus 2. And over here I am just adding a a random noise to this data set. So I've used a rand_n method for of random module of numpy, and this highlighted code will generate an array of 100 rows and one column with the random sample from standard normal distribution. So once this noise is added to our data set, we will have a better visualization of the data. So let me execute this code. So this is the data set. This is a scatter plot of the data set. This seems to be a good two-dimensional data set, and it is very apparent from the shape of this data, this curvy shape of the data, that there do not exist a simple linear relationship between x and y. Therefore, a straight line will never capture the true relationship between x and y, no matter how well we fit it to the training data set. But for the learning sake, let me try to fit a straight line to this data quickly. So let us split the data set to a training set and a test set using the famous train test split method. Let us create an instance of linear regression model and fit it on the training data set. And if we check the coefficients, we have the y-intercept of 4.5 and the slope of 0.69. So this is beta 1. Well, to evaluate the trained model, we will call predict method by passing it the x test to get the y predicted. Do note the shape of y predicted and y test, that is 20 rows and one column, of course. Let's calculate the root mean squared error and R2 score only. So we get a root mean squared error of 2.35, which is of course not good. And the R2 score is 0.4, which means that this model has captured only 40% of variance in the output y using this single input feature x. Let me visualize this by drawing a line, the best fit line. Okay. So over here I have used the plot method. If you see this code, I have used the plot method of pyplot module of matplotlib and passed it all the 100 x values as the first argument and the corresponding 100 predicted y values using the simple linear regression model. Now you can visually see in this graph that the linear regression model has not been able to fit the curve, rather has fitted a straight line. And moreover, since we have predicted for entire data set for better visualization, so you may note that the y-intercept is a little above 2 and not 4.5 as computed above. And this is just a side note for those of you who have observed this. Well, my dear students, you can visually see that the linear regression model has not been able to fit a curvy line, rather has fitted a straight line. And this is because standard linear regression works only when the relationship between the input features and the output label is linear. Okay. In this code cell, if you see over here, yes, in the plot method we have called the x and this predicted values of x. And remember, I have done this on the entire data set. This is important. Anyway, let us move ahead and see how we can fit a curvy line on this data set using the polynomial regression now. Okay. My dear students, polynomial regression is actually linear regression, where before applying the linear regression model, we extract polynomial features from the input features as a pre-processing step. And after that, we fit the linear regression model on all the features. Well, there are two issues that polynomial regression is going to address for us. First of all, the higher order terms will identify the non-linear relationship among the input features and the output label. Then the interaction terms will identify if there exists synergy between multiple input features. Right now our dataset has single input feature. So let me describe what do we mean by higher order terms. And I will describe the interaction terms while doing polynomial linear regression on the advertising dataset a bit later. This first linear regression equation is polynomial linear regression with a degree of 1. Note the degree of the known variable x is 1 over here. This second equation is the equation of polynomial linear regression with a degree of 2. You can note that there are three terms. The first term with the coefficient beta 0 has x to the power of 0, which comes out to be 1, of course. And I have not shown it over here. The second term with the beta 1 coefficient has x to the power of 1. The third term with coefficient beta 2 has x to the power of 2. And similarly, we can increase the degree of polynomial and can get the next equations as well. You can think of this degree as a hyperparameter of polynomial linear regression. My dear friends, there is one question that is normally asked by students while studying polynomial regression, and that is why polynomial regression is called linear regression when we have higher degree of the variable x as shown in these equations. Well, the answer to this question is the values of all the input features, over here it is just 1, that is x, are already known to us. So it is actually the regression coefficients that are unknown, and all the coefficients of course have a degree of 1. Therefore, the relationship of the output y with these coefficients is still linear. That is why polynomial regression is called linear regression or polynomial linear regression. Okay, enough of theory. Let us now try to fit a curvy line on this dataset as shown over here. By extracting higher order polynomial features of x and then applying a simple linear regression model on all the extracted features. Okay. My dear friends, let me once again generate the same dataset using the equation. Let me execute the code of this cell again. Great. Okay. Now to create polynomial features, the code of this cell is first importing the transformer polynomial features from the pre-processing module of Scikit-Learn and creating an instance of the transformer. The parameter degree specifies the maximal degree of the polynomial features. Here, since we have just one feature x, so a degree of 2 will create one additional feature, and that will be x square. Similarly, a degree of 3 will create two additional features, x square and x cube, if we consider only the higher order terms, the squared and the cube terms. And once again, since in this dataset we have just one input feature x, therefore these interaction terms will not be generated. We will talk about the interaction terms when we will see polynomial regression on the advertising dataset, inshallah, soon. And finally, this include underscore bias parameter, if set to true, will create a column of ones and will act as an intercept term in the linear model. So I have kept it false. Anyway, let me create the instance with the name of poly underscore tfm, and let me call a fit underscore transform method on the instance of the transformer class object. And this will of course return a new feature matrix, poly underscore features, consisting of all the higher order terms, interaction terms, and the bias terms as of course specified. Let me show you the shape of this new matrix. So we have 100 rows and 2 columns as expected. Let me verify this by showing you the first row of x. So this has only one value, of course, which is minus 0.4789. And naturally, the polynomial feature matrix will have two values in its first row. Let me show you that as well. Poly features. Okay, so the first value is of course x, and the second value is x square. So we are done with extracting the polynomial features. The remaining steps are simple. First of all, the same old train test split, but this time instead of passing x, we will pass the polynomial features, the polynomial feature matrix that we have generated. Let me execute it. So we are done with train test split. Then we will create the instance of the linear regression model and fit it on the training data set. So these are the coefficients now. Note that the two coefficients beta 1 and beta 2 are 0.87 and 0.84, and the y-intercept this time is 1.9. And these are quite close to the quadratic equation that we actually use to generate the dataset. However, we are not getting exact coefficients, and this is because of the random noise that we added while creating the dataset. Let us now evaluate the model, and for that first we will call predict on the trained model on the x test to get the corresponding predicted values of y. And in this code cell, I'm calculating the root mean squared error and the R2 score. Great. You can see the RMSE has reduced from 2.35 to 1.1, and R2 score is improved from 0.41 to 0.87. So that means by extracting the polynomial features of degree 2 and then applying the linear regression model, we get an R2 score of 0.87, meaning that polynomial linear regression has succeeded to capture almost 87% of the variance in output y using this time x and x square. Great job done. Let's visualize by plotting the curve. Well, this first line of code is making the scatter plot of our dataset. Well, to plot the line, this line is creating 500 equally spaced x values between -3 and +3 and reshaping it to a column vector. Then I am generating the polynomial features by passing this column vector to the transformer object, transform method, which will return, of course, a new matrix having 500 rows, but two columns this time, one having x and the other having x square, that is two features. Then I'm predicting the corresponding y values and finally plotting the line using this x new and y new. I hope the code makes sense. Let me just execute. Great. My dear friends, this is of course a much better fit than the one that we did using the standard linear regression. Now once again a question may come to your mind, and that is how to choose the degree of the polynomial. Here we have kept the degree as 2 because we already knew that the data was generated using the quadratic equation. But in real life datasets, we actually have to find the degree which gives us the best results. So the question is how to choose the optimal degree of the polynomial. Well, here is the code of a function polynomial underscore regression, a user defined function, and it creates a pipeline object that perform the polynomial feature extraction as per the degree passed, do the scaling, do linear regression, and finally plot the curve. We have yet not covered the concept of pipelining, so don't worry much about the code. Let me just call the function with a a degree of, let's say, 2. Great. Before I call this function with different values of degree of polynomial, let me say that this degree is actually the hyperparameter of the transformer polynomial features. So polynomial features, so this is the degree. And let me quickly repeat the difference between the model's parameter and hyperparameters. My dear students, model parameter are actually variables which our model learns at its own during training. That is when you call the fit method. For example, the slope and y-intercept are the parameters of simple linear regression. On the contrary, models hyperparameter are configuration variables that we specify while creating an instance of the estimator or transformer. For gradient descent, it can be the learning rate and number of iterations. And for polynomial feature transformer, it is the degree of the polynomial. My dear students, one cannot know the exact best value for hyperparameters for a given problem. Therefore, you have to find them by trial and error. Let me once again come up and now pass a value of, let's say, 1 as a degree of polynomial and see what's happened. You see, the model has not been able to capture the variance in y if we use a polynomial of degree 1. So this model right now, this trained model has low variance. And there is another related term, bias, which is the inability of a machine learning model to capture the relationship. So we say that this model has high bias as well. A model having low variance and high bias is also called an underfit model. Let me now pass an extreme value of polynomial degrees, let's say 40, and see what happens. Well, by increasing the degree to 40, we have generated around 100 polynomial features and the model has gone quite complex. And now this trained model is trying to fit the line too tight to the dataset. As you can see, the curvy line is trying to touch every point. This model is picking up too much noise from this data. So it has high variance and of course low bias. A model having high variance and low bias is also called an overfit model. My dear students, extreme bias or extreme variance both leads to bad model. Let me give a degree of, let's say, simple 4 and see what happens. So this seems to be okay. This model has now low variance and low bias. So this is a good fit model that can generalize well to new unseen data as well and can also account for variance and patterns in the known training model. My dear students, this is known as the Bias-Variance Tradeoff. And before I do polynomial linear regression on a dataset having multiple features, let me spend some more time to describe this very important concept of machine learning that is applicable to all supervised machine learning algorithms, not only to polynomial linear regression. And this is bias-variance trade-off. Okay. Let me first differentiate between an overfit and underfit and a good fit model with the help of this image. Remember, this applies to all supervised machine learning models, but right now we will be considering polynomial linear regression. Suppose these blue dots on all these three graphs represent the training set of the entire data on which we are training our polynomial linear regression model. Well, this left plot is an example of an overfit model. Overfitting is actually a scenario which occurs when the model is too complex and fits the training data too closely. In polynomial linear regression, this happens when we increase the degree of polynomial above a specific threshold. We also say that this overfitted model has high variance and low bias. This model will give exceptionally good results on the training data as seen over here. However, will not perform well on test or unseen data. Now this plot in the middle is an example of underfit model. Underfitting is a scenario which occurs when the model is too simple and does not fit at all on the training data. In polynomial linear regression, this happens when we keep the degree of polynomial to 1, where it does not capture the hidden patterns in the data. Here this red line says whatever is the value of x, the same is the value of y. So we say that this underfitted model has low variance and high bias. And this model will give bad results on both the training data as shown over here as well as on the test or unseen data. Since this overfit model gives good results on training data, so it is more difficult to identify and is dangerous as compared to this underfit model. So overfitting is more dangerous. So high variance leads to overfitting, while high bias leads to underfitting. Or we can say that once again, extreme bias or extreme variance both lead to bad models. We need to find a balance between the two. Well, this right plot is an example of a good fit model, where we are keeping both the bias and the variance to a moderately low value. In polynomial linear regression, we achieve this by keeping the degree of the polynomial to a value of maybe 3 or 4, I think, in most of the cases. Although this model will not give exceptionally good results on the training data, however, will give reasonably good results on both training as well as the test data. My dear students, I think now you have a fair idea about an overfit, underfit and a good fit model. I think now we are ready to understand the bias-variance trade-off. Well, bias is actually the inability of a machine learning model to capture the relationship between the input features and output label. In this left image, these two bottom circles over here, where the bullets have hit it far away from this red target, we have high bias in both these circles. On the contrary, these upper two circles shows low bias where the bullets have almost hit the target. Similarly, if we vertically see, these left two circles show low variance because the bullets are quite close together, while the right two circles vertically show high variance. The bullets are quite scattered. And we need to achieve the goal, that is low variance, this low variance and low bias. Okay. Let us move on to this right image now, which is a graph having model complexity along the x-axis, increasing from left to right, and along the y-axis we have prediction errors increasing upwards. Remember, right now increasing the model complexity means increasing the degree of the polynomial. My dear students, when you are thinking about overfitting and underfitting, you need to keep in mind the relationship of the model performance on the training data, that is shown by this almost I think blue or green line, versus the model performance on the testing data shown by this red line. So let's imagine that we have split our data into a training set and a test set, and now we are trying to decide what complexity of this model is most appropriate. That is, what polynomial degree should I choose? If you see this blue line, you can observe that as we increase the model complexity, the prediction error goes down and down and down. And of course, this makes sense because when we increase our model complexity, it tries to capture every single piece of noise as well as variance in our training dataset. On the contrary, if you see this red line, you can observe that by increasing the model complexity up to a certain level, the prediction error goes down. But after a certain point, the prediction error on the test data starts increasing exponentially. So our objective is to find this sweet spot, that is the model complexity or the degree of the polynomial in our case, where the prediction error is minimum for both the training as well as the test data. Also note that in case of an underfit model, the prediction error is high on both the training data and test data as seen over here on the left. Similarly, in case of an overfit model, we have very small prediction error on training data and very large prediction error on test data. I hope this makes sense. Now the $100 question is how to prevent overfitting in supervised machine learning algorithms. Well, these are some of the techniques you can use, and of course we will study these in our upcoming sessions, inshallah, in detail. First of all, you can remove correlated features from your dataset. You can do forward selection, where you start with an empty set of features and keep adding one feature at a time. Or you can use backward selection, where you start with the full set of features and keep removing one feature at a time. Cross validation is of course a powerful preventive measure against overfitting that allows you to tune hyperparameters without any information leakage. And these are the different types of cross validation, and the most famous is of course k-fold cross validation. This early stopping is another technique which you use when you are training a learning algorithm iteratively. This is normally used in deep learning. Regularization, well, this refers to a broad range of techniques for artificially forcing your model to be simpler by adding a penalty term to your model. This way the model performs well on unseen data as well. Well, of course, we will study this ridge or L1, lasso or L2, and elastic net or L1 plus L2 regularization in our upcoming session, inshallah. Well, my dear friends, instead of manually choosing the optimal hyperparameters for our learning algorithm, we can use Scikit-Learn grid search CV or randomized search CV. And finally, we can use ensemble techniques that combine predictions from multiple separate models, and the two most common are bagging and boosting. Well, I think that is enough about bias-variance trade-off, the problem of overfitting, underfitting, and the preventive measures. Now let us move ahead and understand overfitting practically using polynomial linear regression on advertising dataset, from which we started today's session. Okay, so let me once again load the advertising dataset. The 3 input feature columns shows the expenditure spent on TV, radio, and newspaper advertisement in thousands of rupees. The output column sales shows the number of items sold in 1000 units, and the dataset of course has 200 rows and 4 columns. Let me separate out the 3 input features in columns X and output labels in Y. Let me create polynomial features using the polynomial features transformer of Scikit-Learn. First we will create the instance, of course. Our degree of 2 will generate 6 additional feature columns this time. 3 square terms for TV square, radio square and newspaper square, and 3 interaction terms. Well, this interaction underscore only is equal to false means we want to keep the square terms as well as the interaction terms. My dear students, sometimes features are only significant when in sync with one another. For example, in this dataset over here, the newspaper advertising spend by itself is not effective, and that we have seen while applying the standard linear regression on this. But it of course greatly increases the effectiveness if added to a TV advertising campaign. Soon we will see this. That is, customer watching a TV advertisement when later reminded through a newspaper advertisement are expected to contribute even more sales. And the interaction terms, that is TV radio, TV newspaper and radio newspaper actually identify if there exists synergy between multiple input features. Anyways, finally this include bias is equal to false. This will not create a column of ones. Fine, let me execute this code and let me call fit and fit transform on this poly underscore transformer object which will return a new feature matrix that I have named poly underscore features, having 200 rows but 9 columns this time. You can check out the shape of this new matrix is 200, 9. 3 square terms, 3 interaction terms and the 3 regular terms, sums up to 9. Let me show you the mapping between the actual 3 input features and the newly created 9 features for better understanding. So this is the first row of the X matrix. I have used iLog method because X is a data frame. And this is the first row of the poly feature matrix. You can observe the first 3 values. These are the same as 230.1, 37.8 and 69.2 in exponent form. And these remaining 6 values, 3 are the square terms and 3 are the interaction terms. You can do the math to verify this at your own time. I hope this is making sense. Let me move ahead and do a train test split on, of course, this poly underscore feature matrix. Do note that I am keeping the same random state so as to have the same shuffle before the split. And this way we will be able to compare the 2 models, one that we trained in the beginning of today's session using standard linear regression and this one where we are using the polynomial linear regression. Let me execute. Okay, note the shape of X train, X test, which have 9 columns instead of just 3. Okay, so next step is to train the linear regression model on the training dataset containing the polynomial features. For this, we create an instance of the linear regression estimator and call its fit method by passing it the X train and Y train of the dataset. Once again, this X train and this Y train is this one, that is the transformed features. Let me execute this and let me show you the coefficients. So you see we have 9 model coefficients instead of 3, and of course just 1 y-intercept. Now the model is trained on the training dataset of polynomial features. Let us now evaluate its performance on the test dataset using the predict method. Once again, remember the X test is the test dataset having 9 features because we have kept the degree of the polynomial as 2. Let's calculate the root mean square error and R2 score, which comes out to be 0.477 and 0.99 respectively. So my dear students, our model has given us better results after this polynomial regression if you compare it with the older results. RMSE has been reduced from 1.46 sorry, from 1.46 to just 0.47, and R2 score has increased a bit from 0.91 to 0.99. Great job done. Once again, my dear students, remember to fairly compare the two results. We must do the trained test split with the same test ratio as well as the same random state as I have mentioned over here. The test size of 0.2 and random state of 54. This we have kept while doing the polynomial linear regression as well as the standard linear regression while doing this trained test split in the beginning of today's session. Okay, fine. My dear students, we have seen that the model has shown improvement with a polynomial degree of 2. One might think that a higher order would improve the performance even more. And this code cell is using actually a loop and checking out the root mean squared errors for a degree of 1 to 5. Well, after importing the libraries and loading the data set once again in X and Y, I am creating two lists over here to store the RMSE on the training and the RMSE on the test data separately. Inside the loop, I am creating the transformer for degree D and then calling fit transform method by passing it X, and it returns of course our new matrix polynomial feature. I hope this is making sense. Then we are splitting this new data set of polynomial features to our training set and test set. These two lines are creating linear regression model and calling fit on the training data set. Then instead of calling the predict on the test data only, this time I am calling predict on both the X train as well as the X test to get the predicted values for both training as well as on the test data. And after this, these 4 lines of code are actually computing the root mean squared errors on both the training set and test set and appending these values in the two lists. I hope this code is making sense. Let me simply execute this code and check out the root mean squared errors of both training and the test data. Well, if you see the errors on the training data set, you can observe that the errors keep on dropping as we increase the degree of polynomial and in turn, of course, the complexity of the model. Similarly, if you see the errors on the testing dataset, you can observe that the error drop up till the degree of 1, 2, 3, 4, but after that it starts increasing. My dear students, let me plot the training error and testing errors against the degree of polynomial for better understanding. Let me just execute this code. Great. Well, we have model complexity along x-axis, which is the degree of polynomial in this case, starting from 1 to 5. Along the y-axis, we have the error. Well, this blue line along which I'm moving my mouse shows the error on the training dataset, while this orange line over here shows the errors on the test dataset. Well, this blue line shows that as we increase the degree of the prediction error goes down. As we increase the degree, you see the prediction error goes down. And this is because when we increase our model complexity, as discussed before as well, it tries to capture every single piece of noise and variance in our training dataset. On the contrary, if you see this red or orange line, You can observe that by increasing the degree up to 4 or up till over here, the prediction error goes down, but after that the prediction errors on the test data explodes. Over here, if you see on the left, with a degree of 1, the prediction error is high on both the training data as well as on the test data, which means the model underfits for a degree of 1. Over here, for a degree of greater than 4, you can observe that the model is overfitting, as we have a very small prediction error on training data shown by this blue line, and a very high or large prediction error on test data shown by this orange line. I hope this makes sense. So the sweet spot for this dataset is a degree of roughly 3, in which case both the bias and variance are moderately low. Great job done. Well, my dear students, that is all for today's session. Hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. I wish you all the best. Happy learning and Allah Hafiz.